Good morning, afternoon, and evening, Madam Seleviawati. This is Group 22 and this is our group presentation for the project. I am Eric Brandon anak BARNABAS, accompanied by GABRIEL GERRARD anak TAGONG, Dylan Yukukwen, MATTHIAS LEMADA anak Peter, and BRYAN Andrew AMIL. To start off, we will proceed with the introduction. In computer networks, there are three kinds of ARQ protocols, mainly stop and wait, go back and selective repeat. Stop and wait is mainly used for noisy channels. It sends the data frame and then waits for an acknowledgement or act to confirm successful data transfer. Go back and is used in networking for reliable data transmission. It ensures data is received correctly and lost or corrupted packets are retransmitted. Selective repeat is used for error detection in the data link layer. Only lost or error frames are retransmitted, whereas correct frames are received and buffered. Flow control is important to regulate data transfer between computers in a network. It ensures the transmitting device does not send more data than the receiving device can handle. Risk of data loss is negated this way.
Hi everyone, let's walk through our experimental setup, where we created a range of network conditions to evaluate the performance of our three ARQ protocols. For test case 1, we simulated an ideal network. We set the environmental to have minimal packet loss alongside a high capacity link. With a constant low latency and a short timeout, we used a single frame setup for stop and wait while configuring a moderate sliding window for both go back and selective repeat. This scenario helped establish a performance baseline under optimal conditions. For test case 2, in this scenario, we created a more challenging congested network by increasing the packet loss and reducing the link capacity. While keeping the latency and timeout unchanged, this test scenario revealed how each protocol manages retransmission and handles degraded performance under tougher network conditions. For test case 3, high latency with varying timeout intervals focused on exploring the impact of network delay. By increasing latency and experimenting with different timeout settings, we aim to understand how sensitive each protocol is to delays and the importance of fine-tuning the timeout intervals to optimize recovery from losses. For test case 4, we investigated how changing the window size affects the sliding window protocols. Here, we kept most parameters constant but varied the number of frames sent in one burst. This test clarified how larger window sizes can enhance throughput yet simultaneously introduce more complexity in handling transmission errors.
Hello, I am Gabriel from Group 22 and will be taking over to talk about the charts and graph for each test cases, where it's throughput, total transmission time, bandwidth utilization, processing overhead, and retransmission count is measured for the three ARQ protocols, which is stop and wait, go back and selective repeat. Alright, to start things off, which is test case 1, low packet loss and high bandwidth. So under the conditions of low packet loss, which is in our case 0.1 and 0.12, and a high bandwidth, which is in the range of 120, 140, and 160 Mbps. In the graph shown, which is in our case right now is example 1, the stop and wait had the lowest throughput across all bandwidth, which is from the examples ahead of example 1, and which is as expected. And as you can see from example 1, it has the highest total transmission time, lack of bandwidth utilization, and processing overhead, with a high retransmission count, which is not good. So even at 160 Mbps, it underutilized the link. But both go back and selective repeat have mostly equal total transmission time. However, go back and showed a noticeable increase in throughput as bandwidth increased, and generally the highest in terms of bandwidth utilization and processing overhead. However, a few retransmissions were still observed due to its entire window recent behavior. Next off, selective repeat consistently maintain an equal or higher amount of throughput with minimal retransmissions, thanks to its ability to only resend erroneous packets. So overall, high bandwidth benefits go back and selective repeat more than stop and wait across all 6 examples, which you can read ahead. Moving on to test case 2, which is high packet loss and low bandwidth. So in this congested scenario, the packet loss is in the range of 25% to 30%, and the bandwidth was low, which is in the range of 20, 40, and 60 Mbps. So from the graphs in example 1 to 6, the stop and wait still struggled severely. The throughput dropped drastically, the transmission time is in an all-time high, it barely utilized the bandwidth and processing overhead, and the retransmission count was high. So, however, the go back N had even more retransmissions than selective repeat due to its cumulative resend strategy, which is wasting bandwidth that's already limited. And lastly, selective repeat outperformed all the other 2 ARQ protocols, again, which is despite the high loss, its selective retransmissions kept the throughput relatively stable. So this test clearly shows how important efficient retransmission is in a noisy environment, which is, as you can see in the congested scenario. You can see the examples from 1 to 6 ahead. Alright, on to the third test case, which is high latency and varying timeouts. Now with latency increased to 200 and 300 milliseconds and timeout set to 5 milliseconds, 10 milliseconds, and 20 milliseconds, the graphs reflect the protocol sensitivity. So first off, the stop and wait, which goes along with the trend before, it showed a dramatic drop in throughput, total transmission time, bandwidth utilization, and processing overhead, and also retransmission count, with increasing latency from, as you can see from the example 1 to 6. And the longer timeout values made it even worse, which is due to its more idle waiting time. Besides that, go back N was sensitive too, but had better resilience with mid-range timeout values. A mismatch between timeout and round trip time either caused the stalls or unnecessary resends. And lastly, as you may know, selective repeat, even under 300 milliseconds of latency, showed a smooth performance with smart timeout tuning. And the lower timeouts, which is due to duplicate retransmissions, but overall it maintained a higher throughput. And this test emphasized the importance of tuning the timeout to match the network conditions. You can see the examples ahead from graph in example 1 to 6. Okay, onwards to the final and fourth test case, which is varying window sizes for the 2 ARQ protocols, which is go back N and selective repeat. So in this final test, we varied the window sizes from 1 to 4, and the data tells us that for go back N, increasing the window size did boost throughput, especially under the stable conditions. However, in scenarios with even a slight packet loss, a larger window meant more retransmissions if a single frame was lost, and it also causes longer total transmission time, less bandwidth utilization, and higher processing overhead. Besides that, for selective repeat, in the other hand, it scaled the best with increasing window sizes. It not only improved the throughput, while also maintaining a relatively minimal total transmission time, high bandwidth utilization, and low processing overhead. And it also managed retransmission efficiently by only resending specific frames. So this test confirms that larger windows help performance, but selective repeat handles the trade-offs better than go back N, as you can see from the examples in example 1, 2, 3, and 4 ahead.
Now, let's move on to the analysis and discussion section, where we interpret the results of our experiments across different network conditions. For the first one, for impact packet loss, for stop and wait, packet loss leads to long delays since it must wait for a timeout before resending the lost packet. Go back N is more sensitive. A single lost packet results in the retransmission of the entire window, which wastes bandwidth. Selective repeat handles packet loss the best. It only retransmits the specific lost packets, which saves times and reduces traffic. So overall, selective repeat is the most reliable in high loss environments. As for impact of bandwidth, stop and wait under low to moderate bandwidth can match the link's capacity. However, on high bandwidth links, having only one frame in transit leads to severe underutilization of the available network capacity. For go back N and selective repeat, both protocols perform much better on high bandwidth links with an appropriately sized window is used. They can fill the pipe with frames and achieve near line rate throughput, though selective repeats consistently manages retransmissions more efficiently than go back N. Next, impact of latency. For stop and wait, it is extremely sensitive to latency. With low latency, the wait times are short and performance is acceptable. Once latency increases, even beyond 100 milliseconds, the frequent send and wait cycle keeps the channel idle, dropping the throughput significantly. For go back N, with low latency, this protocol efficiently refills its transmission window. However, as latency increases, the refill process is slow. When a timeout occurs, you essentially wait one extra round-trip time before restarting the window, limiting overall performance. For selective repeat, with selective retransmissions, acknowledgement still arrive independently, even at higher latency, though recovery of a lost frame still requires a round-trip time. The protocol's ability to continue retransmitting other frames means that it aims to maintain better performance overall. Last but not least, impact of timeout intervals. For stop and wait, it accurately tuned timeouts can prevent unnecessary retransmission and avoid idle time. Setting them too short can lead to duplicate frames, while too long a timeout delays the recovery from actual losses. In go back N, a well-chosen timeout facilitates timely recovery. However, too short a timeout causes premature retransmission of the entire window, and too long a timeout results in underutilizing available capacity. For selective repeat, it benefits similarly. A correct timeout triggers only the lost frame's retransmission, ensuring fast recovery. The trade-off is that an improperly set timeout, whether too short or too long, can either cause duplicate transmissions or delay in recovery.
In summary, our experiments provide a comprehensive analysis of how different ARQ automatic repeat request protocols, stop and wait, go back N, and selective repeat perform under varying network conditions by altering parameters such as packet loss, bandwidth, latency, timeout intervals, and window sizes. We observe distinct behaviors and performance trade-offs for each protocol. The selective repeat consistently offered high throughput and resilience to packet loss, albeit with a greater buffer complexity. Besides that, go back N showed strong performance under low loss environments but suffered inefficiencies with increased loss. Stop and wait, in the other hand, though simple, was highly sensitive to both latency and loss, resulting in significant throughput degradation in congested networks. In summary, these findings emphasize the importance of selecting the appropriate ARQ protocol based on specific network requirements to ensure optimal performance and reliability. So next off, we have part B, which is real-world network implementation.
Hello, now we will begin the part B of our presentation, the real-world network implementation, which required us to design a network diagram for Narmi Sendirian Berhad, a company with 2 office floors, which is Office A in level 1 and Office B in level 2. For part B, our goal was to propose a practical and cost-effective solution that provides reliable connectivity for all employees, supports both wired and wireless access, and allows for guest network isolation for visiting clients. So this is the network diagram that we have designed. At the top of our diagram, we start with the Internet Cloud, which represents the company's subscribed Internet service from local ISP, with a 500 megabits download and 300 megabits per second upload bandwidth. This Internet connection is linked to a router, which converts the signal into a usable format for the local network. And then from the router, it is connected directly to the firewall to provide the first layer of protection against external threats. The firewall connects to 2 Ethernet switches, one for Office A in level 1 and one for Office B in level 2. So each of these switches is responsible for distributing the network to all wired devices within its respective floor. And then the switches will connect the PCs and the printer on each respective floor, which is in level Office A, level 1, we have 15 computers for the stationary employees, 2 printers, and access point. For Office B in level 2, we have 10 computers for stationary employees, 1 printer and 1 access point. Okay. We have also included the wireless access point, or mainly known as WAP, in both Office A and Office B. These are connected to the switches and provide Wi-Fi coverage for mobile employees who use laptops, tablets, or smartphones.
As for my part, I will bring us into the network equipment list, which will be used to build the computer network for Narmi Sendirian Berhad. As you can see here, this is the list item expected to be used for the network. First thing first is the business router that has a built-in firewall. We will be using 2 types of switch, managed and unmanaged switch. Next is the Wi-Fi 6 dual band to support high client capacity. Next is the cable management that we will use in this build. The equipment that we use to manage cable is patch panel that has 24 ports, as we need a lot of cable for our computer and Wi-Fi connection. The cable that suits for our build is Cat6A cable, and for the cord is the classic RJ45 patch cord. Lastly is the list item that used to tie up things or arranging items. 9U rack cabinet is a good investment as it helps in cable management for the Narmi office. Not to forget uninterruptible power supply UPS to protect the system during power surge. So, in this section, I will be present on why we choose this item in the list before. The reason on why we choose the TP-Link ER605 router is it is budget friendly that costs only 300 ringgit. Next is the 2 type of switch where TP-Link SG2210MP switch provide with the PoE or power over Ethernet that able to supply power to the switch without any dedicated power cable. The TP-Link SG100FD is one of the simplest switch that doesn't require configuration. As I stated before, TP-Link EAP610 Wi-Fi 6 is the latest standard wireless network that includes dual band connectivity, also using the PoE as its power source. Panel patch with 24 ports will be a huge help to connect all the Cat6A cable. The reason we are using the Cat6A cable also because it supports up to 10 Gbps data transfer that suits our office use. Cable is not complete without the RJ45 patch cord. 9U rack cable will be a house for some of the equipment like switch and router. This cabinet is important to the office as it is easy to manage for the network maintenance and easy to keep the equipment in one place. Not to forget, it has a good cooling and airflow to keep the equipment cool. The last item is the UPS. This item used to protect the system from power surge. It has a backup battery to maintain operating, which is enough to save work on the computer before turning it off.
And now we move on to the network technology, which is the Cat6A Ethernet cabling. So these are the capabilities of the Cat6A Ethernet cable. So the first one, the speed. Cat6A Ethernet supports up to 10 GB per second, which ensures smooth operation of tools like video conferencing, file sharing, and cloud backups. And then the distance, it can run up to 100 meters per segment, making it perfect for office use without signal drop. And then in terms of reliability, it offers low latency and it is not affected by interference like Wi-Fi is. And then security, since it is a wired connection, it is harder to intercept, so that it can protect the sensitive business data of this company. And then, so why do we choose Cat6A Ethernet cable? The reason is, it is suitable for office use, since it has high speed that can support productivity tools like sharing, meeting, and backups. And also, it is very stable for devices like PCs and printers in the office. And then cost effective. Cat6A Ethernet cables is long lasting and easy to upgrade. And also in terms of the budget, it is affordable and scalable. And now, the question is, why do we choose Cat6A instead of other alternatives like Wi-Fi or fiber optics? So here's the reason. We have made a table to compare the characteristic of Cat6A with other alternatives to make the best decision. First, we look at Wi-Fi, which is the easiest to install since it doesn't require any cabling. It is great for mobile users and short-range use, but it has some limitation because the distance is only about 300 meters since it can be affected by walls. Then we consider fiber optic, which offers extremely high speed and long distance support, even up to 100 kilometers. However, fiber optic is very costly, and then it requires professional installation and it is harder to maintain. For a small 2-office floor like Tarmizi neighborhood, fiber optic will be unnecessary and not cost effective. And then, after this comparison, we choose Cat6A Ethernet. It can provide a balanced solution with up to 10 GB speed, low interference, and is much affordable than fiber. It is also easy to install using standard RJ port, and is suitable for both current and future office needs. So this is the reason why we choose the Cat6A Ethernet cable instead of other alternative.
To summarize this part, on the agenda of cost, we choose the equipment considering cost with good performance items. For future-proof, we choose the most suitable item that can last for a very long time without replacing or upgrading it. Lastly, the security of the network must be ensured to keep the network of Tarmizi dan Berhad work fine without any flaws.
To conclude our project, we would like to reflect on the challenges that we face, how we overcome them, and what we learned along the way. In part A, one of the main challenges was to understand how different ARQ protocols behave under various network conditions like packet loss, latency, and bandwidth. In Part B, it was difficult to decide which network cables was the most suitable to be used, especially comparing between K6A, Wi-Fi, and fiber optic. We also find it challenging to design a secure and cost-effective network while ensuring guest access remains isolated. So, how do we overcome this problem? To overcome these challenges, we run multiple simulation tests and carefully analyze the output to better understand each ARQ protocol. We research about real-world network setup and compare the technical specification of different cables. We also use Visual Paradigm Online to create a clean and professional network diagram, and studied VLAN setup to understand how to separate guests and internet traffic sequentially. Lastly, the key learning point. Through this project, we gain a deeper understanding of how ARQ protocol affect data transmission reliability. We learn how to design a business network that balance cost, security, and performance. Most importantly, this project improved our teamwork, communication, and decision-making skills, and showed us how to apply theory to real-world networking problems. Overall, this project has helped us to grow technically and professionally, and better prepare us for future work in networking and system design. So, that's all from us for this project. Thank you.